So in a test, so for a question like that, especially in FRQ, so how you figure it out, this guy, right? Whether you do it by hand and get 50 or you type it up, right? So that's not something I'm going to get you points for. So you need to get it right. But if you choose to get to this far and you're telling me that you're going to evaluate the function at 50 and set it to negative 150, and after some work, you don't have to mention it. Skip that and get the answer, then you're fine. Right? So you decide whether or not you want to carry out algebra manually or use the calculator. But I do suggest use the calculator to make sure that if you're going to get 5 out of 5, I don't want you to miss that point just because you made some small mistakes. Okay? Because you do have that -3, put it back in, right, to the general form. So then you find the fully factor form of the original polynomial. Now, if you are also concerned that whether or not you should expand everything like they did, well, they did that since, they want to evaluate, right, what this whole thing is when you evaluate the function at 3. To me, I need to see that you guys start with the general form, right, due to the linear factorization theorem, and you can leave your answer in a form -3, which is the true leading coefficient, right, and the product of those 4 linear factors without expanding it is totally fine. Because I hope that you realize how important it is to get a factor form, because if somebody can do that for you, you appreciate how easy it is to read off the roots. Not to mention that we do need the roots or the zeros to plot the graph, right? So I don't see why you have to go with the hard form. Not to mention that I have to do some work to get it. Okay, so now, if you had the mindset that the polynomials are hard to factor, and you thought that not every polynomial is factorable, then you should change your mind, because every polynomial is factorable. It's just that you might not like the form. Okay, the ones that you used to know very well, right? They are, factor kind of nicely, and that's why a lot of people do that. And people don't do the factoring for this guy because they don't see why they have to, right? I mean, of course, nowadays people either they see why they have to do certain things, right? Not too many chances that they get to do it by hand. Now before I move on to 2.5, because I wish to show it to the AM class, but forgot to do it. Let me do it here so that I can have it recorded. It'll just be a quick demonstration with a software that I've been using for more than 15 years. That was way before AI. I don't know if I've showed it to my classes in the fall and spring, but I think that you guys need to know, since a lot of our students are going into STEM, right? So I believe that AI or all kind of models like cloud, ChatGPT, Gemini, whatever models, right, will be very helpful, and you might have to be a master, using them. But at the same time, so far, I think that in industry, people are using, let's say when it comes to math. I mean, you don't have to be a mathematician to use the math software, right? So to be an engineer, then you do have to use them. Bad news is they're not free. So most likely, you are getting them from the company, right? But if you enroll as a full-time college student, they install it on your personal laptop, give you a license, or if you go to computer lab, they have it. All right, so now things, oops, that's big. So let's say if we have to factor, so let's say if I have to write a paper or do some, calculation, but I cannot afford making any errors, right? Even when it comes to something as simple as that, I don't do it by hand. So again, that's like 15 years ago. Just have to type it up. Plus x minus 2, right? But you do have to know the language behind certain software. And this is one of the major one. It's called Mathematica, right? You can tell why they call it Mathematica. And there's another one that engineers use a lot, which is called MATLAB. It's more like doing matrices and simulations. They just call the function factor. It's going to factor for you, right? And it's going to show it up the nice form, right? And that's what we actually do. So as long as you're not a mathematician, you have to figure this out for people. You just have to use the math. So now the problem is you need to know what you want to do. Does it make sense? Because pretty much whatever you want to do in math, you can look it up and Mathematica has it. You just call the function and it will do it for you. Okay? No matter how complicated it is. But let's see something weird going on. So let's say I want to type up this guy. Well, you know what? If you don't like the arrow thing, x squared plus x plus 1, right? You know that it's not factorable in a traditional sense, right? If you were to calculate the root, it will be imaginary. So if I say factor, it doesn't do it. But now you see how smart it is because now it's the 14th version, right? I have 14 point something. I think it's 15 already. But it tells you that, hey, don't you want to think about complete factorization? So it will force it to factor. So let's see what it does. Have you seen cubic root of negative 1? What is cubic root of negative 1? Isn't that just negative 1? How do you know if the cube root of negative 1 is negative 1? You take the negative 1 to the third power to see if it's negative 1, and it turns out it is, right? But how many cube roots should negative 1 have? Or how many square roots should 1 have? 2, then negative 1 should have 3 cube roots. But the reason why you only know negative 1 is because there are 2 imaginary roots. And the reason why it didn't show me negative 1 is this is imaginary. This is something with the I. And the software is smart enough not to show me the i's because if I only need that, I'll call on the function to show me the i's. But that's what we call the closed form to show those ugly things. Okay. So Mathematica does know how to factor it, right? And you know what? You can copy and paste and type it up. And also, you know, people have to write articles. No, it's articles. Let's say, what do you call it? Scientific publication, right? So with all the references and stuff, right? In math and science, you have to have equations. You know that they go by the coding language called LaTeX. I don't know if you've heard of it. So LaTeX, if I get a chance, I'll show you that. But the LaTeX is asking to type up the equation in a very complicated way. And it turns out that for Mathematica, for some kind of software, you can literally see what the equation you want, copy and paste, and change it to LaTeX, and it's going to work out, right? Anyway, so I'm saying that, see that even before AI, we don't do math by hand unless you really, really, really have to. And I don't think that it's ever possible for you to do math in the future because, like I said, you know, if those people in SpaceX sending a rocket to the outer space and doing the calculation by hand, that's not going to work out. Okay. Anyway, let's see. Now let's move on to 3.5. And let me give you the packet. All right, so at the same time, I need to, again, remind you, so test will be next Tuesday in class, let's say the first hour. So when you come back on Monday, I will do maybe some quick review just to make sure that you know, everything is taken care of before Tuesday. But I might have to finish up 3.5 because, you know, it's a rather lengthy topic. Oh, yeah. But I'm very confident that I'll be able to get to a point that you should be able to work out most of the homework problems. So I'll say that if you're gonna have to review anyway, take the chance of working with the homework problems in Pearson, right? But also at the same time, if you could, no problem, work on the test review packet, since there are 2 of them. Chapter 8, right, which is pretty much about chapter, section 8.3. So try some of the problems. Make sure that when you come back on Monday, if you would like to share with us, if there's still some issues with partial fractions, because you never know, right? So since we did that like a week ago, then maybe over the weekend, all of a sudden things doesn't work out anymore, right? So that's the chapter 8 packet. Now, for chapter 3 packets, based on a quiz result, I don't think there will be much concern with the 3.2 and 3.3, right? So we'll assume that you guys are good on that, just need more practice. So 3.4, since there are only 4 questions I picked from a question bank, right? And you can definitely try probably one of the questions based on the packet, right? But we're gonna focus on 3.5, even in a review on Monday, to make sure that you guys are able to graph the rational function, not to mention that, I mean, yes, you do have access to TI-84. That means you can use it to cross-check your result to see that if you graph something that you're supposed to see. But also at the same time, there will be a lot of things for you to keep track of to show me that you know how to analyze the rational function the right way. All right. So it's, like you saw the other day, the question is asking you how many zeros, right? What's the multiplicity? And not to mention, in rational functions, we're looking at not just the zeros, the poles, right? And the poles are really making the rational function harder to deal with compared to the polynomial functions. Okay. Anyway, but the more you do on your end before coming to me on Monday, the more efficient and effective, that review session will be. But the review on Monday will be only either the first hour or the second hour, depends on how smoothly 3.5 goes today. Anyway, now let's take a look at the 3.5. So rational functions. So like I said, it's really still polynomials, right? But unfortunately, you have polynomials on the denominator. So the first thing we have to look into the rational functions is what is the domain, right, of a function like that. But who can tell me the domain of a polynomial function? What do you think it is in general? Ariel? So from negative infinity to positive infinity, right? So all real numbers. So it's trivial. So polynomial functions is the best function that you want to work with in calculus, right? For many reasons, and domain is also one of them. But now you're looking at a polynomial on the denominator, right? And you want to find out if there will be some real number of x that cause a 0 denominator, and you better rule them out, right? So you are still looking at pretty much the all real number set, except for those numbers going to cause the 0 denominators. But from now on, instead of saying 0 denominators, right, those numbers are going to cause 0 denominators, let's again refer to the same terminology that I've been telling you ever since 3.2, the poles. Okay, as you can see that in letter A, there is a pole, right, located at x equal to 3. And the poles are nice to look into when it comes to the graph, but you need to rule them out from the domain, right? So it's all real numbers except for x equal to 3. That gives the domain of the first example here. So you might see the interval notation, right, when the options in the multiple choice in the test specify what the domain is, but please be open to those kind of notation with the curly brackets. I zoom in a little bit, and that's called set builder notation. It tells you the same thing, right? Here, all real numbers or whatever numbers you can think of except for 3. Here, it's just pretty much like Ariel says, you know, for polynomial, you're looking at all real numbers, right, from negative infinity to positive infinity. But now you're skipping one number, right? That's positive 3. All right, so now in letter B, well, of course, you know, you already see it, right? Since, you know, that was just a screenshot. But I want everyone to realize there are 2 poles, right, in the denominator of g of x, which are plus minus 3. And therefore, those are the 2 numbers that you should skip or rule out from the real number set, right, to get you the domain of G. Right? And the last one, the denominator is x squared plus 9. They claim that the domain is all real numbers, as if that the denominator doesn't really matter. And the reason is fairly straightforward, because there's no real numbers for x will ever make the denominator x squared plus 9 0, right? Because it's always non-negative, okay? Not to mention 0, right? It's never going to be 0, since x squared can never be negative unless x becomes imaginary, right? So again, you're just looking at poles, and you rule them out from the real number set, but please be aware of that. Maybe sometimes there's not even a pole, even if you have denominators. All right, so now moving on to the so-called reciprocal functions. But at this point, we should start comparing things that we have talked about back in the 3.2, right? What we know about polynomials. And I believe that we looked into 2 special polynomial functions and used them to remind us how the end behavior of a rational polynomial function looks like. All right, so I think that the first kind is positive or negative x squared, and the other one is plus or minus x cubed. All right, that's a even degree, polynomial with a 0, right? But even multiplicity, right, for the 0. Here you have a odd degree polynomial, either plus or minus, with a 0 with an odd multiplicity, right? When it comes to end behavior, you can go up, right, in both directions, or going down. Or for this guy, it will be either rise to the right or to the left, right, or the other way around. Okay. But now, it turns out that for rational functions, we will also look into something as basic as 1 over x. So that's the simplest kind of rational function, right, with 1 pole, right, and also the pole is at the origin. But later on, we will look into the multiplicity of the poles, just like the multiplicity of the zeros. If I claim that we have a pole which is equal to 0, right, with a multiplicity 1 or an odd multiplicity, right, I think that you should be able to understand it just like, a 0 with a odd multiplicity. But I don't want to keep calling it like the pole with odd multiplicity. So later on, how about we just call it a odd pole? And a pole is not referring to, the odd is not referring to the number being odd or not, right? Because here 0 is an even number, right? But it's referring to the multiplicity. Okay. So like I said, it is the pole, right, that make the rational function a bit harder to deal with. So let's see how the function, let's say 1 over x, the simplest kind of rational function, will behave at the pole or near the pole, right? Because you're not going to be able to get exactly at the pole. It turns out that if you start to evaluate this function by taking x to be, closer to the pole, right, to make the x small, right? So let's say 0.5, 0.1, right? But the closer you're making the x to the 0, right? To, not the 0, 0. I mean the origin, right? The pole located at 0. It turns out that a function will rise to positive infinity. Okay, but from the right. Okay, that means we are taking values of x, right, from the right of this pole, evaluate the function at those values of x, and it turns out that the closer the value you're taking away from the pole, the higher, the greater the value of the function is going to be. So if you take the value infinitely close to the pole, then the function is going to be infinitely large, but stays on the positive side, right? And also the function is going to be infinite positive, positive, right? Or infinite large in a positive direction. Graphically, that's what's going on with the graph of 1 over x, but symbolically, that's how we say or write it. So we're going to use something like the arrow notation. And the arrow means that x is getting closer and closer, or we say x approaches 0, but with a superscript plus. It's not saying that 0 is a positive number, because 0 is not positive or negative, right? But that means x gonna stays on the positive side of the 0. It means you're always taking the value of x to the right of the number 0. That means x, however small it is, it will be always positive. Say positive 0.0001. So when x approaches 0 plus, the function approaches positive infinity, or simply put, infinity. But sometimes, I might end up being putting positive infinity, like leaving a plus sign there. I don't have to. Sometimes I do that because, I find it symmetrical to do the plus sign in front of infinity, right? Then I have a negative sign in front of infinity. But like I said, you don't have to. It's by convention, people don't put plus sign in front of the positive infinity. All right, now, let's say if you decide to take values for x on the left side of the pole, then the x is going to stay on the negative side, right, the left side. So x approaches 0 minus. Still, it's going to get as close to 0 as you want it to, but it will stay negative. Stay negative 0.01, negative 0.001, but as you're getting closer and closer, right, when x gets infinitely close to 0 from the left side, and the function is going to decrease, right, or go all the way to negative infinity. Okay, and that's how you put it. The f of x approaches negative infinity. Okay. Now, remember I said the pole, in this case, 1 over x, right, has a pole with odd multiplicity. So we will refer to the odd pole for this case. And I want to realize that this is how the function behaves when it's near a odd pole. So the function will asymptotically reach either negative infinity or positive infinity, but they are going in opposite directions on either side of the pole. Okay, just like the odd function, right? So we use the word odd, the same reason as the even odd functions. But it doesn't mean that the odd pole always have a graph rise to the infinity on the right, falls to the negative infinity on the left. So I want you to do something just like that. Please be open to the negative counterpart of the reciprocal function, negative 1 over x. So what that means is, if you do have an odd pole, you know that the function is gonna, blow up, right, either one way or the other. But like you saw for the the odd pole with the positive 1 over x, right? So it's gonna go the opposite way But whichever case you're looking at, right, you have the unmultiplicity for the pole that the asymptotic behavior on either side of the pole will be in opposite directions. Okay, so that's something you need to remember, just like the odd zeros. See that the end behavior is going to go in opposite directions. Now, what about the end behavior? That means I'm looking at the graph of 1 over x or negative 1 over x on the far right or far left. Well, as you can see that if you're going to the far right, that means x is going to be approaching positive infinity, right? But now you have a infinite large denominator making a fraction infinitely small, right? But stays on the positive side. That means the function will be approaching 0 with a plus. That means it will still be 0. Well, still be greater than 0. And but it will be as close to 0 as possible. Okay. Now, if you take the x to be approaching negative infinity, so again, you're going to have a infinite large denominator, but in the opposite direction, right? But still, you have the infinite large denominator. The function will be 1 over x will be infinite small. So the function will be still approaching 0, but from the negative side, because the x has been negative the whole time. Okay. Now, let me have the arrow notation. When x approaching a number from the left to the right or approaching infinity, and you can try the same notation with the function values, right? So please make sure that you're not just getting used to reading them, understanding what they mean, but also I want you to use them later on to either explain to me the reasoning behind you plotting or analyzing functions, especially when it comes to the asymptotic behavior. When I say asymptotic behavior, I mean how the function blows up when it's getting near the pole, right? But also the end behavior, right? So we're looking at the far right and the far left, how the function is going to behave. Okay. All right. So now go ahead and take a break. Let's come back in 10 minutes, and we'll work on some, other fundamental functions. 10 minutes countdown. Yeah. Okay. Well, that's an hour. Anyway, if you're gonna do, you gotta do. So, like I said, that so make sure that you did get an official approval, because I do have to check. All right. Is that Dr. Brian? Yeah. I'll talk to her. Thank you. All right, guys. Let's uh, continue our discussion on the rational functions. Because now we are looking at also a pretty fundamental type of rational function. But we don't have a name for it, but you can see that how simple the form is compared to the reciprocal function. Now, of course, you know the major difference between the reciprocal function 1 over x and this guy 1 over x squared is the pole is you know, a even pole, right? A pole with even multiplicity. Now, referring to the arrow notation, or at least that the kind of a asymptotic or end behavior of the graph, as you saw from the reciprocal function, it's pretty intuitive now. Just by observing, you know, how the 1 over x squared will behave if x are getting big or small. All right, so now let's see. Please make sure you convince yourself when x is approaching 0 plus, that means the x will be very small, but still be greater than 0, right? Or, you know, x could be still, you know, pretty small, but stay negative. But either way, the function will have a infinite small denominator, which means that the value will be infinite large, right? Therefore, you know, it blows up, right? Or rise to the positive infinity in both directions. Okay. But you can see that just like the even 0, the even pole rise in the same direction. And I guess that you can imagine if you do have a negative 1 over x squared. Again, you have an even pole, right? But now instead of going all the way to positive infinity, right? It's gonna go down to negative infinity, right? On both sides. And therefore, we wanna always compare, right? Even zeros, odd zeros, and also even poles, odd poles. Okay. Then what about end behaviors? Where x is going to be infinite large. But as you can see that since x is getting squared, right? So it doesn't matter whether x will be positive infinity or negative infinity. So x squared will be infinite large no matter what. And it will never be negative, right? And therefore, you know, the graph will stay always above 0. But the larger you make the x, the smaller the function value is going to be. And therefore, if you're looking at the far right and the far left, the function approaches 0 from the top. Okay. And again, you can expect something similar if you have negative 1 over x squared, but then the whole graph is going to be somewhere, you know, below the horizontal axis. Okay. And And like I said, if we be using the x squared x cubed to remind us how the end behavior looks like for the polynomial functions, please also refer to 1 over x plus or minus 1 over x, right? And also plus or minus 1 over x squared when it comes to this kind of a asymptotic behavior, either near the pole, right, or on the far left or the far right. All right, now, the kind of behavior when the function sort of like a blow up or rise or fall, right, to infinity, can be captured by drawing a vertical asymptote, which is a fancy way to say a vertical line, right, or like a reference line that the graph of the function will never cross, right, but will get as close as it can. Of course, as you're taking the value of x as closer, to the the vertical line, and the closer the graph will be, as it rises to the positive negative infinity. Okay. Now, of course, it will be hard to scroll up and down, but at the same time, you could also look at on your packet. I think it's page 3, right? So there are 4 typical behavior of the function when I get nearby a vertical asymptote. Oh, by the way, you see that you have to draw the vertical asymptote using a dashed line, so that people know that this is not part of the graph. Okay, the solid line usually for the graph of a function, but the dashed line here, a vertical line located where the pole is going to be, tells you that the graph will get as close as it can, but it will never cross it. Okay, so vertical asymptote, or VA, right, are vertical lines located at the poles, and the graph will get as close as it can from either side, rising to infinity or falling to negative infinity, but the graph will never cross a VA, okay, or never intersect a VA, right? Let's put it that way. Now, but please understand that the poles, just like zeros, right, they will be either even poles or odd poles. So if I'm going to number those 4 different behaviors, so let's say 1 and 2, and here's 3 and 4. You see that 1 and 2, right, or 3 and 4 are for the even poles, right, because they have to rise in the same direction, right, either going up or down. 1, 4 or 2, 3, therefore the odd poles. As you can see over there, right, the odd pole is going to have the graph approaching positive negative infinity on both sides, but in opposite directions. Okay, again, so please make sure that you do capture those behavior, and later on when you graph, so always take a look to see if the asymptotic behavior does agree with the multiplicity of the poles. Okay, so now how do we locate the vertical asymptotes, right, or simply put, the VAs? Well, it's as simple as finding where the pole is, but with an exception. So therefore, please pay attention to the wording on page 3. So when locating vertical asymptotes, you will find a VA at a pole, let's say x0 a, if it's not fully canceled by a 0. Right? So, and you will see examples when the pole is canceled by the 0. And again, you will see from an example like what I mean by that. Or just a little heads up, if it just so happened that there was a pole, right, but then somehow it was completely canceled by a 0, instead of looking at a VA, you'll be looking at a hole. Again, graphically, you'll see what it means when we get to the example. Okay. So either VA or the hole, but they will never show up at the same point, right, at the same time, right? So either going to be VA or a hole. So make sure that you do draw one or the other. All right, so now let's take a look at examples on the next page. So we have 3 letters, right? Let's just quickly go over them. So at this point, you just have to know where the pole is, right? If you do have a VA at the pole, or should you expect a hole at the pole? So let's say letter A. So we have 2 poles. They are 3 and -3. And obviously, you're expecting. I guess that I could just draw the graph on the side. I'm just going to sketch it. So there are 2 VAs. One located at -3. The other is located symmetrically on the other side, right? Positive 3. Right, and the function is going to blow up, right? In a way, since those poles are odd poles, right? So remember that for the odd poles, the graph is going to blow up in opposite directions. Okay. Now, of course, we haven't got to the strategy of like sketching the graph of a function, but I can show you what it looks like. I think it's going to be something like this. Okay. Now, do you see that? Since both poles are odd, as the graph getting closer to the pole, it will go either positive or negative infinity, but they will never in the same direction, right? So one going up, one going down. Of course, the reason why the graph could sometimes be above the horizontal or negative or below the horizontal axis. So there are good reasons why we do that, but we'll get to that later. So now let's take a look at letter B. So letter B, the g of x. So let's just be a bit careful. So let's factor the denominator. And hopefully you will get used to doing that. But most likely, for those functions that I do want to graph and capture all the features, so factoring is not really something I'm, super crazy about. But at least for something that's simple, I'm expecting you to be able to factor that. So at this moment, if I do any cancellation, would you say that this seems a 0 at -3? But at the same time, a pole at -3. So of course, you have many reasons that you should cancel the factor x plus 3, right? That leaves you something much simpler. So no zeros, right? Only one pole. But you should be alerted to this kind of cancellation between a 0 and a pole, because that will lead you to most likely a hole. Okay, and therefore, if you go back to the page right before this problem and read what I highlighted, about locating the vertical asymptotes, once again, why am I saying the function has a pole, or has a VA, right, at the pole, if it is not fully canceled by any 0. But now, do you see that the pole at -3 has been fully canceled by the corresponding 0? You're not expecting a VA anymore. So it will be a hole at x equal -3. Okay, so we call it a 0 pole cancellation. All right, please be aware of that. But of course, we still have a pole, right, which is at +3. That means that will be a hole at -3 and a VA, which stands for vertical asymptote, right, at x⁻3. Okay. Now, what does the graph look like? Oh, yes, that I need to get some space here. All right, so the graph will be a VA at 3. And it turns out that the graph stays on top to the right of the 3. And it's going to be somewhere below and reaching or approaching -infinity on the other side. It's like the reciprocal function getting shifted to the right. But if you wonder what happened at -3, okay, so it will be a little circle. That's what you can see from maybe the textbook, or it's not that hard to understand why people put a little circle there. There's a point missing, right? Since you're not supposed to take x to be -3 in the first place, since the domain doesn't even have that point. But we thought that we should have a VA there, right? But do you see that once you simplify the rational function, it does not have a VA because it does not have a pole at the point, at -3, because it was canceled by a 0. Like the kind of a asymptotic behavior that the graph so want to get away from that point on the x-axis. That's what the pole says. Do not get any nearby, right? Otherwise, the function blow up. But if you had a 0 at this point, the function says, please come back and touch the point. But these two things cancel. So you don't have ugly behavior that going away, right? You don't have the graph come and touch it. So let's say it's just a missing point. Okay. But now in the test, if you end up plotting a graph in a TI-84, it's not very easy for you to see where the hole is. It doesn't show the hole unless you know where it is. Okay. Now in the market, you have two popular graphing utility, Desmos and GeoGebra. And for some reason that they have slightly different functionality when it comes to the hole. So I want to show you what it looks like in case you're looking to plotting them. And you should, as you're learning plotting functions, it's always a good idea to, use the graphing utility, right, to make sure that you're thinking the right way, and always cross-check with the actual graph, right? So let's say the Desmos. All right, so let me, where's the share? Here. So what do I need? Here, so x+3. Okay, so now let's see here. At -3, we expect a pole, right? But it doesn't show anything. That means if you don't know there's supposed to be a pole, you're probably gonna miss it. But it turns out that for some reason that Desmos allow you to track it. I didn't realize until this morning. I was playing with it. I was curious, like, if the Desmos going to show us. So it turns out that if you click and hold the button, right, your cursor, right, you slide on the curve. So see what happens if it gets where the hole is supposed to be. It says undefined. Okay, but you have to know exactly where the hole is. Okay, but of course, it's obvious, if it was factored that way, right? Zero and pole cancel. So that's again, I guess that there's some setting I can, fine tune and to see that if it could show up the hole. So then I went to, try that in the decimals, no, in GeoGebra, and that seems a bit nicer. So less investigation needed. Okay, so you see that now. The thing is, again, I don't like, the fact that GeoGebra requires that you have to click and highlight the branch of the graph where there's a hole, but it does show it up, right? So there's no way you can miss that if you just make sure that you click on those parts, right? It is kind of nice. And also I know that since GeoGebra is going to name that function for me, which I can call the function whatever I want, right? So let's say if I didn't realize I will be evaluating the function at the hole, right? So if I do that, let's say -3, it does tell me undefined. Oops. Okay, so at least that you're loaded, right? But again, since we're gonna have to live with decimals for SAT, so please make sure that if there's a way for you to either figure it out right in decimals or find a way to avoid missing the holes, then please do that. And I think that it's not really that hard if you always remind yourself that whenever there is a pole zero cancellation, at least that you should look into whether you should have a VA at the poles or not. Okay. So my AM class, was asking me a question. So they say, hey, what if, let's say G tilde, so a new function that looks like this, x plus 3 over x plus 3 square, x minus 3. Okay, so now my question for you is, should you expect a VA at x equals -3? Then what about the cancellation? How does that work out? Like I do see that if I do cancel the factor x minus 3, right, but not entirely, I still end up having 1, right, just like before, but we have x plus 3, right? One factor does survive from the cancellation. So, I mean, should we have a hole or not? Or should we have a VA? Because that pole is screaming that there seems to be a VA there, right? So now you need to understand there's a reason why. Again, in the wording on the packet, I said if the pole isn't fully canceled by the 0, then you should have a VA. That means a pole at -3 wasn't fully canceled. You see that? You still have it there, so you should have a VA. But the reason why you didn't have a VA, it was a hole because the -3, the pole at -3 was completely canceled, right? There wasn't anything on the denominator to, ask us to put a VA there. So please understand, the difference. All right, so now moving on to letter C. So letter C says you have x squared plus 9 on the denominator. So no poles, right? So if there are no poles, don't worry about any zeros. Oh, sorry, not zeros. Any VAs or holes, right? None of them. HP or holes. Okay, so please understand that For the most of the time, you're expecting VAs at the poles, but there might not be poles even if you have a denominator. So VA, right? The vertical lines that the graph of the function should never cross, right? Period. No exceptions. But something called HA or horizontal asymptotes, then the graph may cross, but we'll see when that happens. Now, first off, this is 1 over x, right? The reciprocal function. So we know what's going on at the pole, right? But now let's look at the end behavior. When a graph reaches far right or far left, so I already explained to you that why the graph will be approaching 0 from top or the bottom depends on whether the x could be negative the whole time or positive the whole time. But I hope that you can see either algebraically, right, later on why this guy has this kind of a end behavior. And to make the end behavior more readable, we will call a line like that, which obviously is the x-axis, right? So y equal to 0 or x-axis is a so-called HA, a horizontal asymptote. It is a line, right? On the far right or far left, the graph will get as close to the horizontal asymptote as it can, but it will never intersect. But only on the far right or far left. Okay. Now, as you can see on whichever page that is, page number 5, right on top, those are the few typical behaviors of a graph approaching the horizontal asymptote. And again, use the dashed line to draw a horizontal asymptote. And as you can see that in the third case, the graph ends up being crossing the horizontal asymptote. Okay, and that could happen. Okay, and I'll show you another example. It does happen, more often than you thought. But again, please remember that VA is a big no. There's no crossing intersection between a graph and a VA, period. But for HA, it might happen. Okay. Now, how do you locate the horizontal asymptote? And again, please, when you study the notes, you know why I'm highlighting certain things. They might not be theorems, right? But they are the strategies or maybe some little tricks. So what you have to do is, not say you have to. So what you want to do is drop the non-leading terms from both the numerator and denominator of a rational function. Okay. So to make sure that we're understanding the terminology, do you guys know the difference between factors and terms? And you might hear me saying all the time, right? Terms, factors, right? So we assume that you guys are okay with that. But now we need to tell difference between these two things. All right. So let's say we have a rational function, and let's make it more complicated than those examples, because all I want to know is to tell the terms and factors. All right, so on the numerator, how many terms are there? 2 terms, right? Because x squared and 1, they're either added up or subtracted from each other. So terms are the things that added or subtracted. So on the bottom, before I do any expansion, how many factors are there? And let's say factors are the things that get multiplied each other. So let's say 6 has factor of 2 and a 3, because 2 times 3 is 6, right? So some say there are 2 factors. Yes. The first factor is a degree 3 binomial factor. And this is a degree 2 trinomial, right? But within the first degree 3 binomial factor, how many terms are there? 2, because that's why we'll call it binomial, right? And there are 3 terms in a factor. You see that terms and factors are relatively speaking. It's like, are you looking at things getting added up or subtracted? Or are you looking at things multiplying, right? So now, back to the example here. Well, on the numerator in letter A, there's no other term except for the 4x, right? And of course, you know, it would make no sense to drop that. But when it comes to the denominator, you have 2 terms, right? What do I mean by the non-leading terms? Or what's supposed to be the leading term? 1 or x squared or 2x squared? 2x squares, right? Not just the 2, it has to be a term. And the reason why it's leading because it has the x to the highest power, right? So drop the terms that's not leading or terms, and please be aggressive. So we'll keep the 4x. Oh, you know what? It's better not to say equal anymore. Let's use the arrow notation. So it's 4x over 2x squared, right? Without a 1. So if you wonder that, what's the point of dropping the terms? Because you're getting something way different from the original expression. We are looking at the end behavior. By end behavior, I mean the x we're looking at are super large. Do you see that? If you make the x super large, let's say, you know, 1,000 or 1,000,000,000,000, right? However large you want it to be, will it make any difference if you add a 1 to a big number? Not to mention the number is infinitely large. So the answer is no, right? It doesn't make any difference. Then why would you keep that 1? Now you see why we like to drop those terms, because by dropping a 1, you see that the rational expression gets a lot more simplified. So you're looking at 2 over x, right? Remember that in this case, x is super large. Or think about this, x is infinity. You have an infinite large denominator, right? What do you think will happen to the function value? Don't you think that it should approach 0? Because x is infinite large. The bigger the denominator, the smaller the fraction. If you have an infinite large denominator, you have an infinite small fraction value, right? But do you guys agree that if x is approaching to positive infinity, then this is actually approaching 0 from the plus sign, right? Anyway, so we realize that there is a HA, which is as simple as y equal to 0, right? Y equal to 0 is a horizontal line, right? It tells you that the function value will be reaching 0, or not necessarily reaching, right? Approaching 0 if we make the x super large. And algebraically, we drop the non-leading terms as we're making the x super large. Okay. Now try the same technique with letter B. So g of x will become 4x squared over 2x, right? By dropping the 1 when x is super large, right? Whether it's going to be approaching positive infinity or negative infinity, no matter what, 2x squared is going to be super large, right? So that becomes 2, right? But somehow that it might be a bit confusing to our students sometimes. Do we have a HA or not? If somehow it was simplified a bit more than we thought, right? You don't even have an x to play with anymore because it just canceled. What do you say? Would that be still a HA in this case? When x is getting super large, the function is pretty much a constant function because it just tells you that a function is 2 or pretty much a 2, or you know what, as large you're making the x, as close the function is going to be, right, like a 2. Therefore, there is AVA, which is y equal to 2. Okay. All right, so now what about letter C? Again, the same trick, right? H of x, you drop the leading term, a non-leading term, right? So you keep in a 4x cube, right? 2x squared, and it becomes 2x. So now my question for you guys is, should there be a horizontal asymptote given the simplified form of the h of x? Like when x is getting super large, super positive, positive infinity, or let's say x is super negative, right, negative infinity, are we expecting the function approaching a constant like 0, 2, or some other constants? Well, unfortunately, what do you think the x is doing? It's either growing or decaying without any control, right? Which means that the function will rise to the right because x is going to be infinite large, right? Or fall to the left if you're making x super negative. So there's no VAs. Oh, sorry, there's no HAs. Okay. But as you will see later, that it turns out that even though that the function does not have a HA, it has something called a slant asymptote. The slant asymptote is a straight line, but it's not horizontal or vertical. It's inclined. It's a line that has a slope. Because you can probably see that, you see the function behaves like a straight line when x is, super large. And, it might be beneficial to realize that, right, when it comes to, plotting or sketching the graph. Okay. But at this point, I hope that, you realize to tell whether you should expect a HA, don't really have to be like going through the math and figure out what the HA is. Do you see that in the first two cases, the reason why we have a HA, that means as you're taking x to be super large, you're able to reach either a constant 0 or a non-zero constant. That's because that the degree of the numerator is less than or equal to the degree of the denominator. Right? Look at letter B, right? The degree of the numerator and denominator are exactly the same, right? So by dropping the non-leading terms, x squared cancel, you're left with a constant. And that's exactly what the h is going to be. But in letter C, the degree of the numerator is higher than the denominator, so you're not getting HAs anymore. You might get some other asymptotes, but at least not horizontal. Okay. But now we have to deal with something that later on it might matter when it comes to graphing the polynomial, especially when you specify what the HA is. Remember I said the graph will never intersect the VA, so the graph will intersect the HA. And let's plot because it will be kind of hard to do it by hand. At least if you want to see the detail of it. So I'm not saying hard to sketch, but it's hard to make it that accurate so you can see all the details. So let me plot the first guy. Plus 1. Plus 1. All right, so do you guys remember that the HA is as simple as the x-axis? Right, so if you want, I can plot that for you so you can see it. There we go. I don't know if you can see that. It's the green line. Right? Let me zoom in a little bit. Oh, you know what? Let's make it less trivial. So I shifted the graph, and I'll plot y equal to 1. Now, There's HA there, right? So if you see, on the far right and far left, you see that the graph is approaching the same line, right? From either way. But the problem is, do you see what's happening here? The graph literally crossed the HA. But it didn't cross the HA on the far right or the far left, right? Because HA captures the end behavior, not the local behavior. You guys know the difference between local and the far right or far left? Somehow? Well, do you know that sometimes people who are doing business, they can file bankruptcy, but later on they might still come back up and become super rich, right? So imagine that the HA stands for the ultimate wealth. Let's say this guy, before he died, he's gonna make maybe $1 billion. We know that at some time in the past or even in the near future, this guy might be broke. So crossing the HA in a local region doesn't mean that it will not respect the end behavior. But it happens local. That means if you set a goal, right? Let's say the ultimate goal. Let's say the guy is going to say, I'm going to make $1 billion, right? You will get there. But don't you think that sometimes you might get closer or farther away? You never know, right? But that's in the near future. I'm looking at the far future. Okay, so that's what I'm talking about. Don't feel like that just because we call it asymptote, just because you have no intersection between the graph and the VA, that you thought that the graph is not going to cross the HA. It could. I already showed you, right? Now, of course, I could plot, maybe, letter B, right? It's going to show up, intersection between the graph and the HA. But here's a pretty interesting rule of thumb, you can actually think about. You can probably just make some sense of it. It turns out, if the denominator has a degree greater than 1, you could expect a intersection between a graph and a horizontal asymptote. And that's why you're looking at, in all 3 cases, well, I didn't mention that in the examples, but in a homework, you will see that if you were to, well, you know what? It's fairly easy to demonstrate that. All right, so before we look at the graph, are you guys expecting a HA from a function like that? Should we have a HA? Well, how do you find an HA? Drop the non-leading terms. Forget about the 1 and -2. It's basically x over x, right? So the HA is y equal to 1, right? Does it make sense if I plot y equal to 1? Right there. Now, if you thought that, oh, should it cross the HA? No, it never will touch the HA, not even locally. But like I said, the rule of thumb is if you have the denominator with a degree greater than 1, let's say degree 2, degree 3, then it's possible that it will cross. All right. So now, what if I make it x squared? Now, but before I do that, if I have x squared on the bottom, would there still be a HA? I'm looking at x plus 1 over x squared minus 2. How do you find the HA? Drop the leading terms. It becomes x over x squared, which is 1 over x. Does this guy have a HA when x becomes super large? Yes, because the function is going to be approaching 0. There is a HA at 0, right? So now let's go ahead and plot it. Now, again, where's the HA as we predicted? 0, right? Do you see that? The graph literally crossed the HA. And there's a way for you to understand it. You don't really have to, but there's a way to see from the remainder, or if you decide to do divisions. But again, it's beyond the level of the course, right? But I'm saying that if you need to predict whether you should have a HA or whether you should have the intersection between the graph and the HA, and it turns out that you need to pay attention to the dividend, not the dividend, sorry, the denominator. And unfortunately, the thing doesn't end there because you have, like I said, slant asymptotes. But in this case, we already had the math part worked out in detail. So if it turns out that you have the degree of the numerator of that rational function exactly 1 degree higher than the denominator, then you will have a slant asymptote, which is a straight line. And the way you can locate it, again, is a little bit different. So all you have to do is the polynomial division. But if we're lucky enough to have a degree 1 divisor, right, with a trivial leading coefficient, you could do the synthetic division and find out the quotient and turns out that the quotient is going to be the slant asymptote, right? Which means that you already know how to find it, but now we just give it a name, right? When it comes to graphing a polynomial function, if you realize that the numerator has exactly 1 degree higher than the denominator, you should expect a slant asymptote, and then you do have to find it through the division. So once you have all the HA, the BA, the behavior at the pole, the end behaviors, right? The symmetries, then you have every ingredient you need to graph the rational function, and that's what we're going to do next time with 3 examples.